Hello and welcome to You'll Be Blessed Education. It is I, You'll Be Blessed, or Mr. Phillips as they call me in the chemistry classroom. And today you are joining me for a lesson on Sig Figs, or significant figures. Now, let me elaborate a little bit more. With significant figures, we're talking about identifying them and counting them for the purpose of using them and applying them in scientific calculations. So let's jump in and start talking about these Sig Figs. So when we're making measurements or performing calculations, the way you report a value tells a lot about how you got the measurement. So we report these values in terms of significant figures or significant digits. I'm going to call them Sig Figs for short. And Sig Figs of a measurement are or calculation consists of two parts, and the two parts are a known part with certainty, and then there's an estimated or an uncertain part, which is usually happens at the end of the measurement. So the last digit of the measurement is usually the most uncertain, or the guess or the estimated part of the measurement. Okay. On this slide, I have a picture of a nail, and I hope we can all agree that this is on next to a centimeter ruler with some millimeter measurements. And so on this slide, I have a picture of a nail next to a centimeter ruler with some millimeter graduations. And we're going to take a look at how we use sig figs to measure something as simple as a nail. Now, I believe and hope that we can all agree that this nail measures at least 6 centimeters. All right. Looking at the macro scale of this version of this picture, we see that the nail is at least 6 centimeters, but we can actually zoom in a little bit more into the millimeter graduations and find out that this nail measures at least 6.3 centimeters. However, we know for certain that this is 6.3. If we look closely, the nail is approaching 6.4, but we know it's not quite at 6.4, but it's past 6.3. Therefore, we're certain about the 6 and the 3. But what we are uncertain about is what is that number in between. And so in scientific measurements, we are actually allowed to make an educated guess between the two lines or the two graduations on the millimeter section of the ruler. So therefore, if you were asking people to make a measurement and ask them to guess what is the measurement between that line, someone might say 6.35 centimeters, another might say 6.37, and then another might say 6.33. And none of those measurements are wrong. Every person who makes a measurement is entitled to some type of guess. And that's where the last part of the sig figs come in. This measurement has two numbers that are certain and one number that is a guess. So it is a 3-digit number with 3 sig figs. So in the last slide, you just heard me say, that measurement has 3 sig figs. How is that going to be important? Well, we need sig figs in order to determine how important our measurements are, especially if we're doing mathematical operations with them. Okay. So before we do that, there are rules to determining the number of sig figs in a measurement. So the concept behind this all is that we use logic to determine the representation of our measurements. So I'm going to repeat that. Logic determines the representation of our measurements. So we use a set of rules based on scientific logic and practices that have been performed in the science labs or in science experiments. And we found a way to consistently communicate how we calculate our measurements, how we make our measurements, how we estimate our measurements, and how we communicate those measurements. Okay? So let's begin. The rules of sig figs. The first rule is non-zeros. Any non-zero digit is always significant. So for example, we have 46.3 meters and we have 6.295 grams. Both of these contain non-zero numbers or non-zero digits, and all of their numbers are significant. So we simply just count the digits, and since our meter measurement or our unit of length, 46.3 meters, has 3 digits that are non-zero, it has 3 sig figs, while the second measurement, 6.295 grams, has 4 digits, and therefore has 4 sig figs. So in this case, the number of sig figs is equivalent to the number of digits that I see in the measurement. Now let's take it up a notch. Rule number 2, sandwich zeros. So that means zeros between non-zero digits are significant. And I call them a sandwich because they are literally between two non-zero numbers. If you consider the zero digits or the non-zero numbers as slices of bread, then the zeros would actually be the condiment or whatever food choice you put in between two slices of bread to make a sandwich. So I call this sandwich zeros. And if we look at these measurements, we have one that is 40.7 liters and another that's 87,009 kilometers. Why are these zeros significant? Well, it comes down to whether or not this number would make sense without zeros. So let's take the zeros out. Well, if you take 0 away out of 40.7, you get 4.7. So in our brain, that just does not make sense. Those two numbers are not equal to one another. Same thing with 87,009 versus 879. Those two numbers mean something completely different when the zeros are absent. Therefore, they are required placeholders, and we need those zeros to be significant when we're making our calculations and measurements. And so therefore, our measurement 40.7 liters has 3 sig figs, 2 non-zeros, and 1 zero that is in the sandwich. And then 87,009 kilometers has 3 non-zero numbers with 2 zeros inside the sandwich, making a total of 5. Our next rule, rule number 3, leading zeros. Zeros in front of non-zero digits are just not significant. And one of the reasons why, now I don't have any slides to support this because I thought I would make another video on this, so I'm still trying to determine that. But these zeros that are in front actually do not contribute to the overall meaning of the measurement, or they could actually be communicated with in another way known as scientific notation. And the zeros are not needed when you're communicating sig figs in scientific measurements. So zeros that are in front, okay, that's where this applies. So we have two measurements, 0.009587 meters and 0.0009 kilograms. Now, both of these measurements have zeros that are in front of non-zero numbers, and we're just going to accept at face value that they are not significant. So therefore, our first measurement in meters has a total of 4 sig figs, while the next one has 1 sig fig. Okay? Simple, but it's important. These rules happen in terms of priority. So rule number 3 is actually the third rule you need to consider when you're actually looking at sig figs because of this next rule, trailing zeros. Trailing zeros are zeros at the end of a number and to the right of a decimal place or to the right of a decimal point. And trailing zeros are significant. So notice in the previous examples, there were zeros after the decimal, but they weren't trailing. They weren't at the end. So they aren't significant. But if they are at the end of a number present with and behind the decimal, the decimal, then they are. So if we look at 85.00 grams, and then we have this miraculous measurement that has no units behind it. I apologize for that. Don't hurt me. But 9.07000000. That's a lot of zeros. But to communicate all of those zeros indicates that there is a level of exactness that is present in the measurement than would not be present if the zeros were not listed there at all. So by saying that this is 85.00 grams, we're actually communicating that we know that this object weighs exactly 85 grams, up to at least 2 decimal places. All right. But then we're looking at, it's actually up to 1 decimal place because the last one is actually a guess. Okay. And then The second measurement, we're probably measuring some unitless thing in physics. Okay, 9.07000. Like all of those zeros is basically just saying, I am so sure that this object that I'm measuring is 9.07 whatever units that, you know, it's without a shadow of a doubt. And so at the end of the day, they're significant. We count the digits. And so our mass measurement in 85 grams has 4 sig figs, while our unitless measurement has 10 sig figs. All right. Now, here is our fifth rule. And I've personally given this a special name in my heart. I call it the ghosting zeros. All right. Zeros at the end of a number, but to the left of a decimal point may not be significant at all. They're optional. The key word is may not. So why do I call them ghosting zeros? It's because we just don't know the origin of the zeros. We have to go back to the original source, back to the person who made the measurement. And without that firsthand knowledge of the measurement, there's a mystery about these zeros, and that's why I call them ghosting zeros. For some reason, if we see a number like 2000, we don't know how many of those zeros are actually significant unless we actually directly communicate with the person who made the measurements. So let's look at this. All non-zero numbers are significant. That's the number 2 in this measurement of 2,000 meters. But because the zeros are not represented with a decimal like in rule number 4, we don't really know how accurate this measurement is. So therefore, depending on who made the measurement and how the measurement was made, it has been communicated that this measurement has 1 to 4 sig figs. So it could have 1 sig fig, 2 sig figs, 3 sig figs, or 4 sig figs. We don't know unless the person who made the measurement tells us himself. But without his voice or her voice, this is all the information we have about these 2,000 meters. And even in the next example, the measurement is 33,490 milliliters. Now that seems to be pretty exact, but because that 1 0 is there and there's no decimal at the end, we still have to consider whether or not this 0 actually really is significant. Therefore, this measurement could potentially have a minimum of 4 sig figs because there's 4 non-zero numbers and a maximum of 5 sig figs. All right. All right, so that concludes all the rules that you really actually need to know about sig figs and being able to identify and count them. So if it is in your interest right now, then I suggest that you would look at this set of problems that I actually just put up on the screen. These are the same problems that I assigned to my chemistry students in the classroom. And so I encourage you to identify the number of sig figs in these measurements and then check your answers. So here's where I make my disclaimer. I am going to pause the video for a second. Well, no, I'm not going to pause the video. I suggest that you pause the video. And if you don't pause it right now, then I'm actually going to show you the answers in 5, 4, 3, 2, 1. Welcome back. I hope that didn't take you too long, but here are all the answers to those problems that I just showed you. And I hope that you found this video to be very helpful to you. I hope you were blessed by it. If you have been blessed by it, please be sure to leave a comment below and also like this video. And if you're really looking forward to improving your chemistry game in the classroom or wherever you are, then I highly suggest that you hit the subscribe button and then hit the little bell button so that you would get a notification every time I upload a new video. I will be uploading videos throughout the entire year related to chemistry, and I'm looking forward to showing you the methods that I use to help encourage my students to learn chemistry and to be successful in the classroom. So this concludes today's lesson. This is You'll Be Blessed. Stay blessed, and I'm out.